Hello students, in this series we are going to study conic sections, that is about parabola, ellipse and hyperbola. So let us have a definition of conic section. It is a locus of a moving point such that it maintains a fixed ratio from a fixed point and a fixed line. Okay. Say, suppose this is S. S is a fixed point. Say HK. HK is a fixed point, and say there is a line. Say this is a line L, whose equation is given by AX plus BY plus C is equal to 0. Say this is a fixed line and this is a fixed point, and a point P is moving. Say this is a point P, moving point. It moves such that its distance from a fixed point, that is this distance, okay, and a distance from a fixed line. So its distance from this line is this distance, perpendicular distance, okay. Let us name this point as M, okay. As point P moves, this M also moves on this line. So suppose point P is here. Now after some time point P is here. So M becomes here and point P is here. So point P moves in such a way that its distance from a fixed point maintains a certain ratio, a constant ratio from a distance from a fixed line, this line. That means PS upon PM is always constant. Okay, we name this constant as E and call it as eccentricity. Okay, so it has a locus like somewhat like this. Point P moves such a way that its distance from point S maintains a certain ratio with the distance from point this line L. Okay, so if E is equal to 1, we call the locus as a parabola. Locus is a parabola. That means if distance from a line and a point are equal, always equal, then that locus is a parabola. If E is less than equal to 1, we call it as an ellipse. And if E is greater than 1, we call it as hyperbola. Okay. So these are the parts of conic section. Say suppose this is a cone. Let us extend this cone in vertical direction. This is a cone. Say, so whatever we study this two-dimensional coordinate geometry, all are a part of conic section. Say if we cut a cone like this, like parallel to ground, so the cross section we will be getting is a circle. The cross section is like this, so it is a circle. Okay, if we cut it like this, okay, then the cross section we get is something like this, which is an ellipse. Okay, if we cut this cone like something like this, say like this, then the cross section we will be getting is something like this, okay, which is a parabola. Okay. And if we cut this cross section like this, then we will be getting something like this, which is a hyperbola. Also we will be getting a point here, so we have a point also. We have a straight line also. Say this is, say if we consider this, then this is a straight line also. So we have all those figures which we study in this two-dimensional coordinate geometry. That is straight line, point, straight line, circle, ellipse, parabola, and hyperbola. So all these are a part of conic sections. So let us first, in this conic section we have already studied straight line and circle. So now let us move to parabola. Okay. So parabola is a locus of a fixed and moving point such that it maintains a fixed ratio, and the fixed ratio is always equal to 1, right? So we have, say this is a fixed line and this is a fixed point. So the fixed point, fixed line, we call it as directrix, and a fixed point we call it as focus. So this is a focus, let us denote it by F, and this line is directrix of the conic section, whatever. And if we join this point and a line perpendicularly, okay, then this line is called axis. Okay, so we have defined three terms: focus, directrix, and axis. Okay. Now for parabola, we have a standard equation. Y square is equal to 4ax. Which is this parabola, whose focus is point A0 and directrix is line x is equal to minus a. The point of intersection of locus, that is this shape, locus, and axis is called vertex of conic. So the vertex of parabola in this case is origin. So this is the vertex of parabola. Here vertex is origin. This is x axis, this is y axis, and this curve is y square is equal to 4ax, our standard parabola. Okay. Parametric form of parabola. How to represent parabola in terms of some parameter. So this point P is say xy, where y square is equal to 4ax. Okay. So we represent x is equal to 80 square and y is equal to 280, where t is parameter. Okay. So t, as t varies, we get point x as well as point y, and this satisfies y square is equal to 4x. So see, y square is equal to 280 square, which is 4a square t square, and 4ax is also 4a times at square, which is 4a square t square. So as t varies, we get point x and y such that y square is always equal to 4ax. So with this with the variation of parameter t, we get a locus. So this is a parametric form. Now, some more definition like focal chord. Say this is a parabola and here it is a focus A0. Any line passing through this focus is called focal chord. Okay. One more term is there, latus rectum. If a focal chord is perpendicular to the axis of a parabola, then this is called latus rectum. What is the length of latus rectum for standard parabola? Y square is equal to 4x. Say this point is A0. So this point must be 4a into a. This point must be a to a and this point must be minus a to a, right? So length of latus rectum is equal to 4a, right? Intersection of straight line and parabola. Okay. So we have a parabola, y square is equal to 4x, and a say straight line. Y is equal to mx plus c. And this is a parabola, y square is equal to 4x. So first condition for line y is equal to mx plus c to be a tangent to parabola, y square is equal to 4x is so this line, if this line is tangent to this parabola, then the point of intersection we will be getting as a single point. So substituting the value of y here, we will get a quadratic equation, and the roots of quadratic equation must be real and equal. So the determinant of that quadratic equation is 0. From there we will be getting the condition c is equal to a upon m. Okay. So in parametric form, equation of tangent. Equation of tangent to a parabola, y square is equal to 4x. So we have y is equal to mx plus a by m is a tangent to a parabola, tangent, right? Where point of contacts are a by m square to a by m, right? So if we write in terms of parameter t, say suppose this is a point P, at square to at for some t, and at point T we have a tangent. Okay. Then in terms of parameter t, what is the equation of tangent? We want to write that. Okay. So here x is equal to at square and y is equal to 2at. So slope of tangent tangent is dy upon dx at point 80 square 280. Okay, so from here we can get dy by dt as 2a and dx by dt as 280, right? So dy by dx is equal to dy by dt upon dx upon dt, which is equal to 1 by t, isn't it? This upon this 1 by t. So slope of tangent is t. So we can write the equation of tangent as y minus y1, which is 280, is equal to m 1 by t x minus x1 80 square. Or we can write yt minus 280 square is equal to x minus 80 square. Okay. So we have equation of tangent as yt is equal to x plus 80 square. Okay. In point form, equation of tangent. Say this is a parabola, y square is equal to 4x, and at point x1 y1 we want to write the equation of tangent. Okay, so the equation of tangent is, in place of y square we substitute y1, and in place of x we substitute x plus x1 upon 2. So we have the equation of tangent as y1 is equal to 2ax plus x. Okay. Now equation of normal to the parabola. Parabola y square is equal to 4a. Okay. A line is a normal to a parabola when at a point of contact, okay, when we draw a tangent, then this tangent must be perpendicular to this line. So this is a normal. Let us write the equation of normal in parametric form. Parametric form, that is at point 80 square 280. We have seen that the slope of tangent is 1 by t. Okay, so slope of normal must be minus t. So equation of normal can be written as y minus 280 is equal to minus t x minus 80 square, or we have y minus 280 is equal to minus tx plus 80 cube, or we have y is equal to minus tx plus 280 plus 80 cube. So this is the equation of normal in parametric form. From here we observe that if for any point x and y, say if for external point x and y, if we want to see how many normal can be drawn on a parabola, so this equation is a cubic equation of third order equation, cubic equation. So its maximum root is 3. So we can have at max 3 normals to the parabola from external point, right? So from here we can say that at max 3 normals can be drawn to the parabola from an external point. Okay. So we have seen the condition of tangent to a parabola and the equation of normal to the parabola, right? In parametric form. In point form, the slope of normal is minus y upon, say at point, say if we want to write the equation of normal, this is a point P, say x1, y1. So y1 square is equal to 4ax1. So we have dy upon dx, 2y dy upon dx is equal to 4a, or dy upon dx is equal to 2a upon y, right? So this is actually slope of tangent. So minus y1 upon 2a is slope of normal. So we have y minus y1 is equal to minus y1 upon 2a x minus x1 as equation of normal in point form. Okay. Point of intersection of normal to the parabola y square is equal to 4ax at points a t1 square, 2a t1 and a t2 square, 2a t2 is given by x coordinate of point of intersection is 2a plus a t1 square plus t2 square plus t1 t2, and y coordinate of point of intersection is given as minus a t1 t2 times t1 plus t2. Okay. You can derive this result also by solving the equation of normals. Okay. So this is more or less theory on parabola. So now moving towards ellipse. We have ellipse is also the locus of a point where there is a fixed point focus and a fixed line called directrix. Okay, such that the moving point P maintains a constant ratio from a fixed point and from a fixed line, right? So here PF upon PM is equal to E, such that E is less than 1. So the locus we get is an ellipse. Okay. Say this is a line. So this must be the vertex of ellipse. Let us name this as a V. This is the focus. Say this is HA. So if we and say this is a point M naught. So if V upon M naught V is equal to E, where E is less than 1. So if we divide line, line segment, if M naught in ratio E is to 1. So we can divide it in ratio E is to 1 internally as well as externally. So we will be getting 2 points. Okay. One is here and another is somewhat here. V dash. So So we have two vertex of ellipse, right? And thus we have a nature of curve like something like this. Okay, and thus we have also two focuses, f1 and f2, and two directrix. Okay, v1 and v2 are these two vertices of ellipse. So standard equation of ellipse: x square upon a square plus y square upon b square is equal to 1. Okay, where b square is a square 1 minus e square. Okay, and focus is plus minus ae 0, and directrix is x is equal to plus minus a upon e. So this is a two focus, and this is directrix. Okay. And the vertex is v1 to two vertex are there, so vertex is plus minus a0 vertices, two vertex. So say this is x-axis, this is y-axis. So we have an ellipse like this, where this point, where there are two vertex minus a0, two focuses minus ae0, and directrix, two directrix which are minus a upon e, x is equal to, and x is equal to a upon e. This point is 0b, and this point is 0 minus b. This is the origin, 0. So we have the equation as x square upon a square plus y square upon b square is equal to 1, where b is less than a in this case. So there are two axes. So we call this axis as major axis, and this axis as minor axis. Okay, fine. Parametric equation of ellipse. So we have a standard ellipse: x square upon a square plus y square upon b square is equal to 1. So suppose say this is a point pxy. So in terms of parameter, if you want to write the equation of ellipse, so we write x as a cos theta, y as b sin theta. So which is the angle theta? This point is a0. So we draw a circle of radius a0, of radius a, okay, and center as origin. So we have a circle somewhat like this. Okay, so this is a circle. Let me draw it more clear. This is our ellipse. Okay, so suppose this is a point P. if we draw a line parallel to y-axis passing through this point P. Okay, so it's cut a circle at some point. Let us name it as P dash. Okay, and say if this angle is theta and the vertex is a0 minus a0. So this equation of circle is, this circle is x square plus y square is equal to a square, right? And this point P dash can be written as a cos theta, a sin theta. We have already seen in circle. So x coordinate is a cos theta, right? So we have x coordinate of this point as a cos theta. Putting this value a cos theta on the equation of ellipse, we will be getting y as b sin theta. So we have this point P as a cos theta, b sin theta as a parametric equation of ellipse, where theta is the angle which is made at the point P dash on the circle. It is not the angle, this angle. Okay, it is not this angle. Theta is not this angle. Theta is this angle. Okay, remember this. This circle is called auxiliary circle. We call this circle as auxiliary circle. Okay, so theta is a point on auxiliary circle. Okay. Also theta is called eccentric angle. Okay. Now tangent to ellipse. For a line y is equal to mx plus c is a tangent to ellipse x square upon a square plus y square upon b square is equal to 1. The condition is that c square is equal to a square m square plus b square. Okay. So we can write the equation of tangent as y is equal to mx plus minus a square m square plus b square under root, and this is derived in the same fashion by putting the equation of y, okay, is equal to mx plus c on the equation of ellipse. We will be getting a quality equation, and the roots of quality equation must be real and equal, so that we will be getting only one point of intersection. Okay, and the point of contact is point of contacts solving those quality equation, we will be getting the roots of the quality equation. Okay, so the point of contact we will be getting as a square m upon c and b square upon c. Okay, minus b square upon c in this case. So now in point form, equation of tangent, this is an ellipse at point P x1 y1, equation of tangent. In place of x square we will be substituting x1, and in place of y square we will be substituting y1 to get the equation of tangent. So x1 upon a square plus y1 upon b square is equal to 1. Okay, this is the equation of tangent in a point form. And in parametric form, in place of x1 we substitute a cos theta, and in place of y1 we substitute b sin theta. So our equation reduces to x a cos theta upon a square plus y b sin theta upon b square is equal to 1. That is x cos theta upon a plus y sin theta upon b is equal to 1. Right? Now equation of normal. A line is normal to ellipse. Say this line is normal to ellipse. At point of intersection, if we draw a tangent to that ellipse, then this tangent must be perpendicular to this line. So we call this line as normal to ellipse. For ellipse, standard ellipse, x square plus a square, y square upon b square is equal to 1. The slope of tangent, if we want to find, then we have to find dy by dx. Okay, this is slope of tangent. So differentiating this equation, 2x upon a square plus 2y upon b square dy by dx is equal to 0, or we have dy by dx as minus 2x upon a square upon 2y upon b square. So 2 will be cancelled, which is equal to dy upon dx is equal to b square upon a square x upon y, right? Minus with a minus sign. So this is the slope of tangent. So slope of normal can be written as minus 1 by slope of tangent, which is equal to a square x upon b square y, right? So we have y minus y1 is equal to a square x1 b square y1 upon into x minus x1. So this is the equation of normal. And if we want to write the equation of normal in parametric form, then we will be putting x1 as a cos theta and y1 as b sin theta simply.